Advent of Code in F star. We are about to start day 22. Let me get a couple things set up. We had quite a crowd show up yesterday. We had two separate raids, and I can only apologize that I was so on the wrong track. I mean, I should correct that a little bit because I did manage to get both the second star. My solution was almost correct. It's let's see. So I had bugs in the predecessor states function, and that was really the most complicated part to get right. Almost everything else was correct, but this had some fairly fatal flaws. Um, but it took so long to run that it was kind of hard to find them. So I did write some code to dump out every single evolution of the vector, the state vector. And so I was planning to try to turn this into a visualization, but I did not start the stream in time to do that. But yeah, this approach can be made to work. I think it's a lot slower, both because the vector is sparse and because this is not a particularly efficient way to do the transitions. Um, but I did manage to make it work more or less in the shape it was in last night, just with correcting the predecessor state. So one of the problems is I said, well, if the game's already won, then there's no next state. Well, that meant every game that was won was just dropped on the floor, except for the very last time period. So the total was much too low. Um, so yeah. I did find a nice visualization from Maxwell B. Joseph of the outcome of the game. So here are all 273 billion parallel games grouped by score differential and end position and the number. So I thought that was nice. So hopefully I will not go down the route of overcomplicating things tonight. Uh, I did. Where did that go? I looked back at the documentation bug I found, and mainly it was that I didn't understand it. But there was a small bug, and I've submitted a PR for that. So it was not as big a documentation bug. It was just hard to understand. But reading it a second time showed what's going on. All right, here we are with day 22. Oh no. Need to reboot the reactor. All right. So we've got 100 by 100 by 100 cube. Oh, for now, ignore cubes outside of this region. All right. That's a little scary. Um so I think we can anticipate what's coming in part 2. I think in part 2 we'll probably be asked to do the larger range. So, should we write the more complicated version first, or is that a bad guess? It seems to me that I guess one of the things they could ask for part 2 instead of how many is ask about the state of a particular cube. And that would require a much different approach. All right, let's copy the input. And I think I'm going to simplify the input before before trying to parse it. That this sort of thing is not too difficult. It's just a pain with f star. So let's replace. Let's just make this a comma separated list. All right. That will be easier for us to parse because we already have all the facilities to do that. So what we don't have is a three-dimensional array with an update function. So one option is to use, let's see, 100 by 100 by 100 is that's 10 to the 6. It's a million entries. And I don't have an integer range function. I do have a I do have a natural number range function. All right, let's do this the simple way, because I'm not sure I'm up for doing it a complicated way anyway. And so our simple way will be to flatten it down into a single million element vector list. It's 10, 100 times 100 times 100. Oh, that's 101 times 101 times 101. Yes. All right. All right, let's think. Is there a simpler way? Okay, so instead of keeping all the cells in memory, we could process the list multiple times once per cell, once per cube, right? So we could say is -50, -50, -50 in the list. Well, it's in if we match each, if we have more on, if the last command that applies to it is on. I mean, if we're going to iterate over a million things, we might as well do it that way. Am I talking myself into something dumb again? No, I like this. Let's, okay, so that's going to be our strategy, is I don't know very many geometric algorithms, so if we have to do something clever for part two, we may be stuck. But I think this'll work. All right. So what should we write first? Let's write the record type for the cube. So all right, on and off. What shall we call these things? The step, a reboot step. All right. I like this because it's, well, I'm not sure I like it. I like this because we're not doing a lot of looping, coloring things in, which could be, in the worst case, as big as the entire square. So C min, C max. All right. So let's say, okay, so oh, and we need the cube state. All right. So Sure. Well, I saw a curly brace and I went right back into go mode. Uh, okay. So x min less than or equal to x and x less than or equal to x max and whoops. All right. Point in rules. All right, let's see. So in current state and steps is a list of reboot steps, and that returns a cube state. All right, so I pluralized it. All right, that was the problem. All right, so an empty list is the current state. So if then change the state to head.value and go through the tail. Else, leave the current value alone. Not prove termination. Okay, so the default order is lexicographic order of the elements, and current flips back and forth. So we just need to tell it we're decreasing the steps. Okay, good. So now we need to count. Turn right. Let me just make sure we're looking for the right thing. How many cubes are on? I mean, what are we doing here? Like a few 100 million operations? I can't believe the right. Okay, I can't believe the right approach is to simulate the whole million element matrix. So that's just off the table. The question is, should we be like doing something cool with a region tree, or researching geometric algorithms, like what's the intersection. And if it was intersection, I could believe there's something nice, but intersection and difference is going to complicate it a lot. I mean, one optimization we could do is search from the back forward and just take the first result that we find. That would be kind of cool if we could prove that worked. All right, let's write the boring version. No, let's write the fast version. All right. All right. So if we're empty, it's just the default. That's a keyword. All right. So decrease. All right. If point in step, then we return head dot value. Otherwise, we keep looking. So we can write this in with higher order functions. Where's my help? Is this find? Yeah, there we go. All right. So find point in step XYZ in reverse steps. So we match that. And if it's some step, then we return that step's value. Otherwise, it's none, we return the default value. All right, I like that. So can we prove that they're the same? All right, so given all of these, our argument, our claim, I'm gonna have to do this recursively. So apply rules fast if XYZ default steps equals apply rules of X, Y, Z, and the default value and steps. All right. Oh, well, we need a different format. We need to say this is the insurer's clause. All right. Match steps with. All right. If they're both empty lists, they both should be default. It should be able to reason that out. Um, and let's just make sure it can. All right. It's happy with the base case. So I don't think this simple thing will work here. Yeah, that's not going to work. All right. So we know that I have no idea what we know. Do we have any lemmas about find? Okay. Good. We might need that. That's the only property we've got. So for example, it doesn't tell us that we find the first such element. So, all right. So this says for a short list. All right. All right. So getting from this to the head is pretty clear in this case. To the longer is pretty clear in this case, and we may just have to spell out that these two are the same. All right, so this is gonna swap the value of default and current. So that's gonna be a problem because they don't match. They don't match the condition anymore. What do we know about reverse? It preserves the length. It preserves membership. Yeah, I'm not really seeing a lot to help us out with order. If I was going to prove this to a human, I'd say the last time that current changes is the last element of the list that matches, and it changes that value, which is precisely what we do here. We find the... Okay, so we could break this down by whether find is going to find something else. So we could say, in the case where it's not there, yeah, as usual, the proofs are too hard to do right away, which is unfortunate. So that's what I would like to get better at, but all right. I will leave this be. So let's parse the input, and all right, let's iterate over it. Let's do the count first. So I'm going to do this as a Taylor recursive loop. All right. So what we're going to say is we're going to put bounds on these so we can do termination checking. And say this. All right, it's just going to be X. This is silly. They're all the same. So let yeah, coordinate is an integer where between -50 and 50. So we've got our steps, and we've got a count of cubes. And that is a total function returning nat, and we'll probably have to do a termination proof. So let apply rules to the current. Why did I reverse that? the default is off, and there's our list of steps. All right, so if current z equals 50, all right, so if all those are true, then we're done. And so we were going to turn, okay, let's make this an expression. Let's make this 0, 1. Then all right. There may be a bool to natural number function, but I don't know what it is. Let me do this the other way. Order. Which is gonna be easier to do the termination proof. It's gonna be the order I originally wrote. All right, so we've gotten all the way through X. Sorry, we've gotten all the way through Z and all the way through Y. So count cubes. X plus 1, 0, 0 steps. All right. So we've reached the end of, we haven't reached the end of Y yet. Go back to 0. In the last case, we haven't reached the end of Z yet. So that's the, all right. Let's see how that flies. Oh, phooey. All right. I deleted my nice constants. Do as I say, not as I do. All you junior programmers out there. All right. So our termination condition is that we decrease that tuple. So we work through our z's, and those get closer and closer to 0. No, they get other way around. And okay, these are messed up. These are not 0, these are minus 50. All right, so we start at 100, 100, 100, 100. Z goes up and this number goes down. All right. Should, and because we put, oops. This is one of the more annoying things about F star, is it doesn't. You have to enclose negative numbers like that, because otherwise it's parsed as the operator minus instead of a unary minus on the string literal, on the numeric literal. All right. That's it's a big loop, but that's fine. I hope. All right. And now we need to parse these. So when was the last time we did that? Oh, parse. Okay. That's a complicated one. Let's just day 4. All right, I guess I'm just doing this from more or less from scratch. So parse step. All right. In fact, we're gonna have to do this a little funny because the first one is not. Okay. One thing I find strange is that this function is a total function. So it does something. If it's not a number, I don't know what. And that seems kind of antithetical to what F star ought to be doing. So we can use that as is. It's just kind of gross. I think it'll be 0, but I don't know. Could be anything. Undefined behavior. All right. All right. So I'm going to have both of these split the string. Nah, no, I should just do this right. All right, so. All right. All right. So if length of the tokens is less than 7, and none. All right. Else, let val equals parse on off. The first one. All right. And now we're going to let no, we're gonna map our function over the tail of the tokens. All right. And so our result is value is v just read them off. It feels like there should be an easier way to do this by unpacking the list, but we'd still have to sign them in one at a time. So no need to get fancy here. But we could template match on a fairly large list if we really had to. All right. There's some places we can just put the record constructor, and some places you have to put it in parentheses. And I don't know which is which yet. I just let it tell me if I screwed up. Oops. All right, I just want this for the pattern of match step line. So if it's none, not else. It's a some step, then we're going to return S and the rest of them. And we want them in, we wanted to preserve order. All right. So open the file. All right. So cubes, start everything at -50. Steps 0 to start. All right, let's see how it does. Oh, that is the wrong day completely. Oh, that wasn't so bad at all. That seems like a very large number. I don't trust that number. That is more cubes than we've got. Yeah. All right, let's try something simple. For given an empty list, everything should be off. All right, good, good. Um, all right, let's try. Is it going to give us a problem about that? Okay, well, that was a little encouraging. Uh, that now it says everything's on. Only we'd completed our proof, I'd have more confidence that this was right, but I can't think what might be wrong. Let's try replacing. Okay, since we got both, we can just substitute one for the other. All right, so it's not that. Somehow is on is true for every single address. So I'm wondering if the quality is not true. I would have hoped it would have warned me if. No. Hmm. Okay, so we saw. What's that to? That was 0. All right. Well, if worst comes to worst, then we'll just debug it. So get a million log entries, which isn't ideal, but we can handle that. Oops, okay, we need a semicolon, and I'm just gonna do Head steps again. All right, it says everything is on. Did we give the wrong default value? Wow. All right, so point in step has to be returning true. Oh, what am I doing here? All right, yeah, it returns true for every point. Duh. All right, so this needs to be. All right, the problem was that I had Xmin and Xmax defined, and so when I didn't put step dot in this function, it still compiled. All right, that should be a lot better. Okay. All right, 590784. That looks good. Just want to check that. Double check that. Okay. Um, so let's write a proof of its correctness. So if x is less than step.xmin or x is greater or, not and, then point in step xyz step is false. I did not manage to write it correctly even that time. All right, good. Let's get our real input and transform it. Right. Equals becomes a comma. All the dots become commas. All the y equals go away. All the z equals go away. Yeah, it takes longer with the longer rule set. But that wasn't too bad. All right. All right. So I guessed wrong. I guess we do have to engage in some geometric reasoning. Be real nice if none of these intersected. Could we check that? I mean, all these, no, all these, no. So my hypothesis is that none of these go through the origin, through the square in the middle. And that would simplify things a lot. So maybe let's do some exploratory work. All right. All right. So what is our test? So x has to be between All right. I've actually done this for work not too long ago. X min. All right. And we can consider each coordinate separately, right? These are going to be 3 points that satisfy all the individual bounds, or there won't be. So, all right, and so that should be equal. So for that point to exist, this has to be less than x, which has to be less than that. So s1 dot x min less than equal to s2 dot x max, and the other way around, s2 dot x min less than equal to s1 dot x max. All right. So let us say complain because we didn't. All right. So our lemma our model of correctness for that function is intersects s1, s2 if and only if there exists x, y, and z such that and the point is in s2. All right, I think it's not a colon, it's a dot. I don't know why it's a dot. All right, it couldn't prove it by itself, or the function's messed up. All right, think I think we're fine. Does it find it easier to do one direction? No. All right, so can we define that point? So if it exists, it's going to be it will be the larger of the two minimums, or the smaller of the two maximums. right? So whichever of these is smaller, it'll already so it's say S2 is smaller, will already be in S2, and we've guaranteed that that is above S1, so it's in S1 as well. All right. Let's let's show this direction. I picked min rather than min of the maximums rather than max of the minimums just because min is built in and max is not. All right, so there's been something I've been meaning to use here. I added a link to it in the wiki. So if we want to prove n exists, all right. This might be a little difficult. All right, so we're going to introduce exists. Huh. Wow. All right, so what it says is F star classical sugar exists intro not found. So this switches to something from that package, but doesn't automatically. All right, so we need a squashed proof. All right, this is really if we're working with squash types. Um, let's just try. Here we've got one, but it's implicitly part of the lemma. So maybe just stating that should be enough. All right, where does the proof go wrong? So I said, what I said it out loud is S0 is less than, all right, my assumption is S1 and X0 is less than or equal to, all right, are you with me so far? No, why not? Is it because the properties of min aren't in the environment? Let's look for a lemma. Oh, no, that's the F sharp implementation. That's the wrong way. All right, we picked X0 to be the smaller of these. Is that our problem? So okay, so if it's S2, if it's S2, then this follows. And then it must be that S1. Okay, all right. So the missing piece is we didn't guarantee that the ranges are non-empty. So the theorem is false. There might not be one because maybe they're out of order. So we'll add those. So S1 to X min, X max. Oops. Yeah, so that was my implicit assumption, but we didn't actually guarantee it anywhere yet. And without that, our computation, oops, is incorrect. Nope. Okay. It doesn't know. That seems fairly obvious to me, but it doesn't know it. All right. Or min xy equals y. So I don't know why it can't figure it out in this case. It might be that it doesn't have enough fuel in this case, but that seems. Oh, I used and again. All right, so that was probably not necessary. All right, yes, it knows the first part. Good. Okay, so it got here. It didn't get here. So I think here what we have to use that intersects is true. these not sufficient to prove it? So how can that not be true? That is one of that is one of our okay. So I did this wrong. Uh, that's the problem. It was not actually introduced. All right, that's our problem. Um, I mean, can it do the whole proof now that it's by itself? Now that's right. No, but we should be able to cut out these intermediate steps. Yes. Okay. Yeah, so the problem was I was writing the proof as if this was true, but what we had to prove was if it's true, then blah. And so the one we either needed to do some work with the classical logic module to say create a function that takes and intersects S1 and returns our theorem, and then conclude from that that the lem was true, or just move this up into the requirements. All right. So what I was gonna do is print out which ones intersect. So did I write a combinations function? Yes. So I'd probably put that in my library. All right, that doesn't work. I don't have a for loop. I have f star dot list dot map I iter. So if intersects then let's print it out. All right. If we're gonna have to do more of this, we can adapt this into a real print function, but else do nothing. Oh, we didn't finish type checking that all. Yeah, we're good. All right, lots of intersections. Tons of intersections. But this is interesting. The big coordinates only intersect other big coordinates. The little coordinates only intersect other little coordinates. So that's a nice property. So what I'm thinking is we can compute a disjoint representation. We can divide the cube up. All right. When we intersect two rectangles, two cuboids, whatever they're called, two rectangular solids, we must get another rectangular solid, right? There's no way it can skew. The intersection, but the difference, the intersection's that way. Okay, but we could come in and take a bite out of a bigger cube. So we'd be left with the outside region, the intersect region, and our outside region, and the first and third would not be rectangular. So the decomposition isn't trivial unless it happens to be because of how the data is set up, but it doesn't seem like a good thing to count on. So I really don't want to decompose into non-rectangular pieces. So it's possible, it's just more work. So what I would like to do is decompose our entire space into rectangles, into rectangular solids. And for each one of those, we can run our original algorithm with slight modifications to say, is everything in that rectangular region on or off? And then we can add up all the sums. But that requires doing the decomposition. The other thing is we can do inclusion, exclusion. Not really. I don't. That'd be good if we were only turning things on. But since if we turn it off, we've got a problem. Again, unless the input has some structure that's not immediately obvious. I guess the decomposition into non-convex shapes is fine as long as we can count how big they are. So what I'm thinking is, so we say we have a two-dimensional analog. As long as we know how many are in B, but not in C, then we should be fine. So we can calculate how do we do this decomposition? Do we calculate lots of intersections? So let's see here. Yes, we would calculate A intersect B, and we would remove that many squares from both A and B. But then if we had D, that was maybe like fully within C, we'd have to do inclusion, exclusion. So what would this look like? So we'd have to say the volume of A by itself is But that's too big. So you'd have to do inclusion, exclusion the other way. No. I mean, it's a set difference union everything else, but we don't. That doesn't give us its cardinality. That's not likely to be it. Well, it's late enough we could start peeking at what other people are doing. I'm not too proud to do that. All right, so I'm looking at somebody else's solution. Gnarf, who joined the live stream later. Okay, yeah, I see the idea here. So we process. All right, so if we got A, B, and C, so A is lit and B is not and C is lit, then everything in all right, so everything in C we're going to add. Right, and we can go on to the next one and say, well, nothing. And then we go to the next one and we say, light everything that is not part of some region already processed. So it's sort of like the fast algorithm I'd done for the simple case. And so what we need to do is okay, so we need to filter this elements in B and C to just the stuff in A, and we can recursively call the same function to do that. All right, let's try. Okay, so we need a we need the intersection of two cuboids. So this is just the min on every dimension. No, let's get this right. So it's all right. Let's do. Whose value do we want to use? Let's use the first one. All right. So the min is going to be the max. So we need max after all. Oh, heck, I don't know where it went. Okay. Oops, that's not x2, that's c2. All right. So, okay, let's. All right, so our base case. Okay, so our base case, as usual, says there's nothing, and that has zero that are on. So if we've got we need to maintain what we've seen before. So this is going to be priest. All right. So if C is not lit, then we don't have to do anything yet. So if and I think we better put it uh we better preserve the order so that we process these in the same way. And so if we take one off the front of steps, it has to go onto the back of previous steps. Is this a true fact? Um, all right. Otherwise, and this is where we're going to use the recursion twice. All right, so it's the same thing. So we're going to do area of C minus so we don't want to count anything that is either already lit or was turned off below us. So that should be the area the volume of everything All right, so we've already counted everything in C. So anything in A intersects C, we don't want to count. Anything that was turned off in B, we don't want to count, but we can't just add those. We've got to do inclusion exclusion. So I think there's an elegant recursive way to express that. Maybe we don't need to do it in reverse. Okay, yeah, that works a lot easier. Right, so I think reverse order might be a little more helpful, but so uh, right, so we want to recursively use the original list. So now our structure has the we're doing the same thing every time. So here we need to take say what is lit in the previous steps, but we need to intersect that. So right, so anything that the previous step said was already lit and which lies within C, we're not going to count, and we'll add C to its list in order, preserving the order. All right, so let's try that. Okay, we need area. Which should be positive or 0. So Um, return, which I don't think we can prove without the assumption that all these are ordered. So we probably should have put that in right from the start, is that x max is greater than, all right, so x, but we can't do that in a record. All right, how much is it worth to me to fix this? Right, because we tried that before. A record can't use a have a refined type that refers to another record. Oh, we can. All right. And maybe I didn't get the syntax right before. Except that's gonna cause a problem here. How does it, can it know that these are the same? What if we say, see, this is something that has to intersect? Okay, great. That worked out well. So our intersection, uh, we defined these so that they're always well defined now. They always have non-zero area. And so we could intersect two things that don't intersect and get zero area. All right, so now we should be able to prove that the area is greater than zero because the area is x min is x max minus x min times y max minus y min times z max minus z min. All right, and it says yes, that's always positive. All right, so we should be able to make our model lots cheaper here, right? Because all those are now built in. Great. So, all right, we defined area. Now we need to find trim. Okay. I think thinking ahead a little bit, we're going to want to say the length of the result is less than or equal to the length of the input. All right, so if bounding and CS intersect, then we're going to add the intersect with, and we want to keep the value of the first argument. So that is going to be, let's not create trouble for ourselves here. Oh, all right. We didn't start the recursion. Match CS with empty. It's empty. Else. So if the head intersects our bounding box, then trim that to the bounding box. So this condition matches the order we did here. Otherwise, you have to tell it that intersects is commutative. We could give either order. Then trim to bounding tail. Else just trim to bounding tail. All right, good. So I think, all right, couldn't prove the termination. So we've got this tree structure, right, where we process the first one off steps, and then to process the next one, we have to call that recursively. And then above that, we have to call the previous list recursively, in the worst case anyway. Hopefully in real life we'll do better than that. So in the worst case, all right, previous steps is getting longer. All right, so when steps is getting shorter, we're fine. Right, it is specifically this call where steps may have gotten very short, and then we give it a very long call to work with. But okay, so so our metric is going to be tuple. So length decreasing length of steps is always fine. And then sometimes we need to make a call that decreases the sum of the two, which ordinarily won't decrease. Nope, that didn't work. Oh, we just need the lemma there. We need fun facts about Snock. Yes, that is not introduced automatically. So let's add it. Nope, not good enough. All right, so what's going on here? I think that is unchanged. Right? I think that's invariant. All right, so agrees with my assertion, but still disagrees. This, this, if this is it, I'm going to be very upset. Okay. I don't know what it means to have the comma there, but I'm annoyed that that is valid syntax because it's virtually never right. Okay. So this is okay. So it's not the termination check. It's the it can't prove that this subtraction results in a positive number. And that is, in fact, a fairly deep result. So, could we prove it inductively while we're solving this? so it's true that okay, so we know that this is always less than the area of the sum of everything in here. Uh, and that's a very complicated type to write. So I'm just gonna let it think that's an integer. Okay. Now, if he'd written this one before, it would have been less code. All right, let's see if this works. Oh, that's part one. Oh, what couldn't it prove? Oh, okay. Yeah, the extra conditions we added. All right, so we just got to check them. All right. Wow, that was fast. But not correct. All right, so there's got to be. All right, let's try. Oh, uh, Let's try just the first two. Is there tail nth index? I'm not seeing a first end. First end. All right. So yeah, that's just completely wrong. Oh, there we go. Yes, these definitely intersect. So that is 47 minus 5 times 2 minus 31 times minus 33 minus 19. Okay. I think the problem is we're not accounting for outs. Yeah, this is wrong. Okay. How can we prove that? I don't know why doing this math made me think of that, but so yeah, we processed A. We can't just add it to the stack. We actually have to turn off everything we did. So this is, it doesn't light anything up, but we still have to. Anything that was lit by our previous iterations is now not lit. in the region bounded by C. All right, let's try that. That looks exactly, it doesn't, it's not exactly our previous number, but it's pretty close. But it's not right. Oh! The example's not the same. All right. All right, that would help. Okay. If nothing else, Advent of Code is a demonstration of the power of the only thing that we know makes better software, and that's getting enough sleep. Hillel Wayne has a great talk on what we don't know about software engineering, and about the only thing we do know that makes a difference is getting enough rest. All right, that looks like the right number. 2758. No, it's not right. It's closer. All right. All right, let's go back to checking our math here. All right. It could be also that I didn't save. This is minus 5 minus minus 44 times minus 27 times 14 times 35 minus 14. Whoop, whoop. It's not right. All right, so the intersection is x equals minus 5 to 5, y equals minus 27 to 21, z equals minus 14 to 33. So that is minus 5 minus 5 times 21 minus 27 times 33 minus 14. Okay, so the result from that should be 23,600, and it is not that at all. Okay, well, good to know. It means the bug appears early rather than late. So let us check. It can't be input parsing, I think, because we got the name. We got the first part right. So max minus min throughout. Okay. Is the order wrong here? No. It's consistent. Okay. All right, what can we do to get F-star to actually help us here? So let's see what we can start to prove about count cubes. So All right, so if C is on, then count cubes C empty list equals area of C. All right, good. And if it's off, then it should be 0. Okay. So if it's already on, then adding it on again should not have any further effect. Good. All right. So we believe that if we've got 2 of them, that are both on, then the area, that should be area C1 plus area C2 minus area of uh, intersect with C2, C1. Okay, and intersects C1. All right, so this is reasonably complicated. Okay, so this is good because it tells us that the logic is correct in count cubes, but since our numbers don't match up, that we've got an easy but hard to spot bug in all right. If intersects, screw it. intersects area intersects with C0, C1. Parsing error. Alright, what's going on here? Oh. I may have been running the wrong part anyway. Okay, we did get the right value that time. All right. I'm gonna try rerunning it just in case the problem was that I had not saved the file. Ah, phooey. All right. Two 275. Yeah, it's not right. I mean, we can try this, but I'm pretty sure it's wrong. Yep. All right. So let's see if it's 1 is on and 2 is off and they intersect, then we should get C1 minus the area they intersect. All right, that is also correct. So if you've got a problem, it must be on a later iteration. I guess the thing I'm worried about is, that I've checked several times, is that trim2 might rewrite the value, but I think I got that in the right order. So I mean, we can write that as a lemma. So if they intersect, requires intersects, trim to C1 of C2. So and the head of this dot value equals C2 dot value. All right, yeah. It's nice to have the proof, but that doesn't tell me where I'm screwing up. Uh, min, max, 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 min, 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 max, max, min, max, max. All right. Areas all looked correct. I don't need that anymore. Oh, we built our lemma out of it. All right. Trim limits area. So if our bounding box is reboot step and a then um, So this is probably going to be too challenging to do as is. You're going to have to at least recurse. Uh, okay, got the base case. So I don't think we know that intersect. We haven't shown that intersect reduces the area. So let's try that. All right, so intersect with and these need to be less than or equal to. All right, I think we'll probably have to give it some help here. Let's give it a shot. All right, so all right, so all our maximums get smaller, and all our minimums get larger. And those are all the inputs to All right, is that enough? Uh, all right, so I suggest that that means okay, so all three factors get larger. Ah, so the all right, interesting. So why doesn't it think that is the case? Um, it should follow from so it should follow from this and should follow from this and oh, I got these all backwards. Every term gets smaller, not bigger. All right. I mean, I'm just carrying through the chain of logic one step at a time. Agrees with me so far. So this should be true. And if not, maybe we need a limit to prove it. Huh. Didn't go out to lunch? Is it still working? Still turn along. Application failed. Timed out. Why doesn't it believe this is the case? Alright, that is interesting. Should all be positive because shouldn't it? Like if we have 5, if we got negative 100, then the minimum still has to be bigger, so it's big enough to go positive. Oh, alright. We'll I know what the problem is. Oh, I made the mistake in my hand calculation. It's an off by one error in area. So the 0 to 0 has size 1, not 0. Okay. Will that fix our proof? Doesn't look like it. Yeah, so I made the same problem calculating my test case as I originally made writing the code. Um, so if we fix that, oh, like I made a mistake. Yeah, so I don't know what we could have done here, but let's run it and see what happens. So it could be that that is what prevented our proof from working, right? If one of these terms go to no, I can't. I think the proof would still work, even with the wrong area formula. All right, enough of that. Uh, okay. Let's at least finish our proof here that it should, it should be the case that intersect. All right. If intersects. All right. So if we could prove that, then the theorem we were working on was true. We got a lot of proofs done today. Just not the one, not the one I needed to find my bug. That would explain why we're only off by a little bit. Why the first few digits were correct. All right, 275,851,49. All right, yeah, that was our problem. Hurrah! Okay, well, wasn't too bad. I don't think we're gonna make a very good. Wow, that is better than I thought. I can see there's a fairly sharp drop off here. So a lot of people did not manage to copy somebody else's algorithm like I did. So, other than making stupid off by one error, I was actually pretty happy with this. We managed to prove a lot of small things that we thought were true, even if I don't have a model for the great thing. These are all sort of like property-based testing cases. But we didn't have to put in a particular value. It actually proved that they were true for any values that we could have given that satisfied the requirement. And I think that's pretty cool. I would definitely prefer this to randomized testing. Of course, I would prefer it with property-based testing. You actually get an example where it fails, and here you just get, oh, I couldn't prove it, which is somewhat less useful. Um, yeah, so what didn't we manage to prove? We didn't manage to prove this, which I don't know why. It should just be math. Um, so maybe this is a case where giving more fuel would help, just because we got such deeply nested stuff, but I don't know. Is there something we can prove about this that is more general than our two? I mean, what would be nice is to tie our old definition and our new definition together, right? So if we could use our part one code and say, if we manage to run part one on every point that might possibly be lit, then it would give us the same answer as count cubes. Uh, so that would be a challenge, but that would be a very interesting thing to do. Is tie part one and part two together that way and say, and that would be what catches our area bug, right? That we wouldn't be able to prove it because our area formula was wrong. So as usual, the proof that would be most useful is the most complicated to contemplate writing, um, which is unfortunate. But okay, I'm gonna I'm going to end the live stream. Thanks for staying up with me. Uh, thanks to all the sponsors of Advent of Code. That includes my employer, Akita Software, and we just updated our jobs page. So check it out, akita.software.com/akitasoftware.com/jobs. I think I've mentioned the developer advocate role, but we put up a job listing for that. And we put up a picture of the team playing double deck pineapple Chinese poker. So maybe I'll do a video about that sometime once I figure out the strategy. Sorry, I wasn't screen sharing. Yes, there's our jobs page. There's our smiling faces, the open roles we have right now, and there's us playing poker. So good night, happy Advent. I will see you tomorrow.